EE-341 linear control system. Up to now, we cover the major part of the analysis in linear control systems, and the most important part of the analysis, and definitely it will be helpful in also the part of designing is the root locus. And in this lecture we will try to cover the fundamentals of root locus and how, and also define the basic rules which will be helpful to draw the basic of the root locus. Uh, Again, outlines again it is with the fundamentals of root locus and also the comparison of closed loop and open loop transfer function, which is already covered, and try to define few properties of root locus and as well as examples to solve some complex functions, and also define the some basic rules which will be helpful to draw the root locus, and also try a simple example. This part of the root locus based lecture is the analysis and also the designing part, and it will be helpful to design the controller and how to set the values of gain also. Try to define the root locus and the various aspects which will be help which will be used in various ways to understand the basics of root locus. And actually root locus is the graphical representation of a closed loop poles. Usually open loop systems information is given and we use that information to draw the root locus, and in which will be the representation of closed loop poles, and it will be the analysis and designing for the stability and the transient response. And when we find the root locus, then we can visualize the aspects related to the K and how these effects will be helpful to understand the transient response and the stability. Actually, it is the qualitative description of the control systems. Closed loop systems actually depends on the location of the closed loop poles, and the system's design parameters will be uh, will be helpful, and it can be adjustable uh, for the different values of the controller and the designing parameters for the closed loop poles, and the location of the closed loop poles also actually varies accordingly. Root locus actually it is the analytical method and the graphical representation of the closed loop transfer function with the designing by using the designing parameter, which is usually the gain factor of the when the open loop transfer function information is given, and it is the path of roots. It is a more mathematically and more understandable definition that it is the path of roots of a characteristic equation in a S plane when the system parameters changes from 0 to infinite. So when it is the path, when the open loop transfer function is given and we have to find the closed loop transfer function, and then from the closed loop transfer function denominator part is the characteristic equation, and from this characteristic equation if we put equal to 0, then we can find the roots of the equation. And there is a dynamic parameter which is usually k, and if we change that k from 0 to infinite, actually not infinite, it is close to infinite. When we change from 0 to some maximum value, then the roots of that equation may be of any order changes accordingly. This is the root locus. Few part of the lecture is just a review from the previous one, that we have a system of a closed loop, and where this close is complete by the feedback, and this feedback is a negative feedback, and usually in our control systems we use a negative feedback, and the transfer function of that feedback system is h of s, and the forward transfer function is kgs. So the closed loop transfer function is given by this relation. So this is the important parameter to understand the details of the root locus. And here we are talking about the characteristic equation. This is the characteristic equation. This is very important, and if we find the values are the parameters of this equation, when we put it, it is equal to 0, because here this k is a variable, this is a dynamic variable, and if we change this dynamic variable from 0 to some maximum value, then the roots of this closed loop transfer function, actually it is the poles of a closed loop transfer function, is changes accordingly, and this is the root locus. And I will try to elaborate in detail about the root locus in different forms, so try to understand the concepts in any way which will be helpful to draw and to understand the root locus. So complete picture to present the closed loop feedback systems. So here we have forward transfer function kgs, and there is a actuating signal here where E sub a, and this is the output, and this is the reference or input value, and this is the feedback transfer function, and corresponding closed loop transfer function is equal to this one, and this is the representation of in the form of closed loop transfer function. K is the open loop gain factor. In the whole concept of root locus is the K. This is the gain factor. Actually, after we studying the control systems, at the end we understand this K is a just proportional controller. So here we are talking in another way that this is the open loop gain factors, and this and from the closed loop transfer function, this part, the whole part of the denominator is the characteristic equation, and only this part is the open loop transfer function, because we already usually this is the open loop transfer function is only g, where h of s is equal to 1 and usually k equal to 1. But if k is not equal to 1 and even feedback transfer function is not equal to 1, then open loop transfer function is like this one, and this will be helpful to understand the concept of root locus. And usually we draw the root locus by using the when the open loop transfer function is given in terms of k, and this is important concept. And again, this is the characteristic equations of the closed loop transfer function. To just give a just a quick review from the last lecture, that we have that g is given and h is if given, then we can find the open loop open loop transfer function is like this one, and we will try to analyze this part in the form of a way that we will be able to understand the root locus if we analyze this relation in this format. And there this k is variable, and s plus 1 times s plus 3 there are two zeros, which one is at -1 and another is at -3, and these both are at the open loop zeros. and there are three poles. One is at 0 and other is at -2 and third one is at -4. And in this case there are two zeros in an open loop transfer function, and there are three, okay, sorry, there are two zeros in open loop transfer function and there are three poles of a open loop transfer function. And how this relation will be helpful to understand the root locus. So be focused and try to understand the concepts. Again, to just review the previous concept, that if we put all these terms into a closed loop transfer function, then we have, this is the closed loop transfer function, and this is the, from the closed loop transfer function it is shows that these s times s plus 2, this is the pole of a open loop forward transfer function, and s plus 4 is the feedback transfer function's pole, and these are acting as zeros in a closed loop transfer function. And similarly and the zeros of open loop transfer function, no, it is the part of a closed loop poles but dependent on the k. So this is important. And again, if we change this value of k from some minimum value, which is maybe a 0 value, if we put equal to 0, then there is only three poles. One is at 0 and other is at -2 and third one is at -4. There are three poles. And similarly, if we approach to the infinite, so these values are way and in between. And this concept will be clear in the next part of the lecture. So understand the basic concepts related to the characteristic equation. So this closed loop transfer function here, this is the characteristic equation, and this part is the open loop transfer function which is dependent on the k, and this is the characteristic equation, and this equation is the equation for which we are finding the roots dependent on the values of k. This is the root locus. So path of the poles in a closed loop with the variation of k is the root locus. The variation of k is the root locus. Whole story of the complete portion of root locus you can understand from this slide, that we have a closed loop transfer function where this is the open loop transfer function and this is the characteristic equations. And in this equation, if we put equal to 0, then we can find that there, if this is equal to 0 and if we put these values here and here, if we put equal to 0 and take the LCMs, and we find the values of s which are existing at 0, -2 and -4, these are the rows. This is the starting point. This is the starting point of the root locus. It means open loop, in open loop transfer function, poles of the open loop transfer function is the starting of the root locus, where k is equal to 0. This is the starting of a root locus. And similarly, if we take this k is equal to infinite, maybe some maximum value, and then taking the common here, and because this k is directly not equal to 0, and if we manipulate the relation, then we can find that there are two roots which are existing at the -1 and -3, and this is the end point of the root locus. It means Root-Locus is starting from k equal to 0 and ends at k equal to infinite. In this case, starting point is there are three poles in an open loop transfer function and ends at equal to at zeros of the open loop transfer function, which is equal to -1 and -3, and there are three locus lines starting from the 3 points and ends at the 2. It means the third line will be ends at infinite. Usually we have number of poles are greater than the number of zeros in open loop transfer function. So usually this happen, and this is the concepts which is the related to the Root-Locus, and this is the starting point of the Root-Locus. The whole story of the Root-Locus is clear from these statements. This is the just wording statement of the previous results, that Root-Locus is the plot in a complex plane as a function of k, and from k equal to 0, Root-Locus is the starting point, which is the starting of from the position of the poles of a open loop transfer function. And similarly, k equal to infinite means it is the end point of the Root-Locus, which are the points of a zeros of the open loop transfer function. And in terms of closed loop transfer function, and if we change the value of k from 0 to infinite, then the path, the line is changing from the closed loop pole and ends at the open loop transfer functions. And similarly we can say, and it is the open loop poles and terminate at the open loop zeros. Both are the same concepts. Actually, Root-Locus is the path of closed loop poles. Actually, with the variation of k, open loop poles are position of the open loop poles are not changes. Position of the open loop poles is the starting point, and closed loop poles are changes accordingly. And closed loop poles are changes when the values of k are changing from some minimum value to some maximum value. So to plot the Root-Locus, just it is the factorizing the polynomial in the denominator of a closed loop transfer functions. And if we don't have a computer or any machine, we are unable to factorize these higher order systems. We are able to analyze and solve the first or second orders, but if these are higher orders, then we are unable to solve. So this is the, so what is the quick way to find the path of the closed loop poles? So Root-Locus is the quick way to understand the path of a closed loop poles. It is starting from the open loop poles and ends at the open loop zeros, and this is the path of a closed loop poles. This is the Root-Locus. From here we will try to understand some mathematical manipulations of some complex functions in terms of magnitude and angles. You can also try these type of concept by using any complex number mathematics and complex functions mathematics from any mathematical book. So if we have some g of s is the function which is equal to the ratio of the product of the positions of zeros to the product of position of the poles, So here we can directly find the values of a zeros and positions of the poles if we put equal to 0, and z1 is the position of the 0, and this may be a real value, may be a complex value. If it is a complex, then n minus s is also a complex function, and n s minus z is a complete complex function. If z is a real value, maybe -2 or -3, usually we are taking these type of functions, then s is a complex, so it is the subtraction of a complex number from some real number. And similarly for the other in terms of poles situations, and it is the product, it is in the form of product. And this product form, if we find the function value of the function, then it have some magnitude and phase angle. For example, we have a sum x plus j3 in times 3 plus 9 j and so on, divided by the 2 plus j11 and times and so on. If we have this type of function, then we can easily manipulate the whole function in terms of magnitude and phase. And these magnitude is actually we can find just taking the mod values, and these mod values actually representing the length of the product of the zeros and to the product of the poles. And we can try this type of example, and definitely you will be understand. And where theta is the which theta is representing the complete angle of this function. So if we find the angle of the numerator terms, then this is the, if the product, if these are the product, then we can just find the angle is adding. And similarly in the denominator part, and these are the related to the angle of the zeros and angle of the poles. And denominator part, if we take in the form of numerator, then we can take this some negative value. And these stuff of mathematics already you have done in many courses. And this is the mathematical form to represent the angle of this complex. So if this function is some closed loop transfer function, and how to represent this closed loop transfer function in terms of the angles and the magnitude of the function. For example, this is the some characteristic equation, and this characteristic equation, if we take 1 plus the open loop transfer function part sum equal to 0, then this is the characteristic equation. And from this characteristic equation, from here we can show that open loop transfer function is equal to -1 and the magnitude equal to 1. So we can normalize it. So this is the one fundamental property related to the transfer function of a closed loop transfer function. And if we find that open loop transfer function and take the magnitude or mod value of that complex part, then it is equal to 1. If we somehow verify, then we can say that it is open loop transfer function, magnitude of open loop transfer function. And similarly, and the phase angle of this one is equal to some -1, and -1 is equal to 180 degree. And so it is variable part which is dependent on the k. So this k is a odd multiple of the 180 degree. So if we find that the sum of the open loop transfer function, the total angle, then it is the always multiple of the 180 degree. So it is the second major conclusion in of the property related to the closed loop transfer function and the open loop transfer function. And this k is varies from for positive and negative values, and from, if we find that, and this k is equal to, if we take the mod value, then it is equal to 1 over the g times the s mod value, and it is equal to 1 over m, as we placed, as we find in the last part of the lecture, and this m is already defined here. So it means if we want to find the value of k, it is the equal of the product of pole length to the product of the zero length. So this is the definition of k. Directly or graphically we can find, or some numerically ways we can find it. Okay, these some fundamental relations will be helpful to find or manipulate the complex functions, and how to find. And there is some conversion from rectangular to a polar and polar to a rectangular conversions, and these this is the representation in a rectangular form, and this is the representation of a polar form, and this is the another way to represent this nuclear form. And if we want to convert it into a rectangle into a some polar conversion, then this is the way to convert, and similarly vice versa. So these are the some fundamentals of manipulations of some complex numbers, and this will be helpful to find the values of the complex functions. These mathematical manipulations will be helpful to understand the data simple concepts related to the complex functions. And here we have a closed loop transfer function with unity feedback, and open loop transfer function is k times s plus 3 times s plus 4 over s plus 1 times s plus 2. There are two poles in open loop transfer function, and there are two zeros in a open loop transfer functions, and the closed loop transfer function, and this is the open loop transfer functions, and this is the closed loop transfer functions, and these are the positions, are the locations of the poles. And definitely ultimately maybe in next lecture we will solve this the same examples to find the root locus, because here is the some additional concept required which is not covering in this lecture, is the breakpoint and other concepts related to this one. And here we want to find that s is equal to minus 2 plus j3, whether this point is lying on a closed loop or not, for the values of k or not. So this is the concept, and let's see. So just this is the some vector representation of the point. So one pole is at -1 and other pole is at -2, and third pole is at third zero is at -3, and other zero is at -4, and we want to find the values of this one. One way, if this is the scale graph, one way is to find that we can find the length of these vectors, and by summing up we can find the values of k and so on, and also verifications by taking the sum of the angles. And other way to find the values that let's see. So this is the for this zero, if we solve for this zero at this point is simple. This is the L1, which is the simple representation or solution of a point for 0 at -1. So this is the point, this is the value of s minus 0, this is the s minus 0. Maybe it is a pole or 0, but here we are talking about the 0, and its imaginary part is 0. Only just taking the sum of real values, which is equal to +2, and the imaginary part, which is +3, and find the conversion and we can find that the magnitude of this line is 13 under root and angle theta 1 is 53.30 degree and so on. And similarly we can find the length of all the lines at this point by using the same criteria. Again, this is also the for other zero, similar this is for the and other pole and also for the other poles. And uh, by taking the sum of the angles, which is equal to minus 70. So if we find the sum of the angles, which is minus 70, so it means that this point is not lying on the root locus. So for here k is not, so it not justified that characteristic equation. So this point is not on the lying on the root locus. And similarly we can find and take another example, another points, and we can find that point is, this is the point, and that point is lies on the root locus. And if there is, and this is lying on the root locus, then we can find the length of k by just taking the product of the length of the poles to the product of the length of the zeros. So this is the way to find the length which is already manipulated, and at this point, which is an other point in this part of the example, it is 0.33. So this is the value of way. Another way, this is the way to find the values of k when the operating point on the root locus is given, and vice versa. We can find the another way around. The next example, we find that there is a 1 0 and there are two poles in the forward transfer function, and the feedback transfer function had 1 0 and one pole lies at -8 and -2. So if we find the closed loop transfer function, then the part of the open loop transfer function which is dependent on the k, how these poles are varies, let's see through the simulation. If we simulate these, the closed loop transfer function with the different values of k, these values are changing from k0 to k20. So if we change the values from k0 to 0.5, so these poles are lying here, and up to, if we change the values at 0.5, then these poles are lying in a complex plane, and further we increase the values of k, and these location of the poles are changes accordingly. So one pole is path of one pole, it changes in this way, and symmetrically the other poles positions are changes with the variation of k by increasing the values of the k. So this is the concept related to the root locus, and next we will describe in detail. And I add the previous examples just to manipulate or to give a reminder, and here we have, and I am taking the some snapshot of from the book, that we have a camera systems which is shown in the figure, and we have definitely have a look in many times around us. Can we automatically follow the object, and tracking systems monitors the pixels and the positions of the camera to the center of the changes, and root locus techniques can be used to analyze and design the effect of uh, loop gain and the system transient response and the stability. And here we have a amplifier, which is K1, and the monitor and the camera whole systems, which is around about like the some motor based systems, and the transfer function of it is equal to K2 by S times S plus 10 and 10. So this is the input is the position of the object and output is the position of the camera. So closed loop transfer function is equal to like this one, where K is equal to the product of K1 and K2. Definitely it is another constants. How we can manipulate by changing the values of K? Let's see. Analytically, we find the table that for different values of K. For example, if we take this K equal to 0, then we have two roots of this closed loop transfer function, and these roots representing the poles locations in a closed loop transfer function. And definitely if we solve that, one pole is at 0 and other pole is at -10. And similarly, if we change the value of K, and we find that poles are changing their positions. So this is the next position of the first pole, which is at -9.10, and the second pole, which is already at for value of K equal to 0 is at 0, and next position for K equal to 5 is -5.53. And similarly, if we change the values of K, and we see that at K equal to 25, both poles are at the same positions. And similarly, and after that, we see that if we change the values of this greater than 25, then we find that these poles are in a moves in a complex plane, and because we have a second order system, so these are in the form of pair. So this pair and this behavior is very important in the form to understand the root locus. So this pair is changes accordingly, and the length of these are equal if we manipulate distance values, and if we change the values of K. And for values K equal to 50, one pole which is starting from the position of -10, and now in a complex plane it is at the position of -5 plus j plus j5. It is on the upper plane of a left half plane, and similarly, and the other pole is at the lower end. So this is the manipulation, and graphically we see that with the variation of K from when K is equal to 0, one pole is at -1 and one pole is at 0. And similarly, if we change the values of K, one pole is from 0 and other pole is -1 and moving toward this point. At value of K equal to 25, these two poles are lying on the same point. And if we further change the values of K, one pole, we don't know out of two which one is moving in the upper side and other one is the lower side. There will be additional techniques to understand the concept, but at this stage we are unable to understand. And this is the plot of a root locus, and this diagram is the root locus, showing the root locus, and these figures taken from the book. And this is the pole placement, and with the variation of K, and this is the root locus, and it is similar. Shows this is the similarity shows that root locus is actually changing the values the positions of the closed loop transfer function, and starting point is K equal to 0 and end at K equal to infinite. But in our case, it is we are taking some limited values of K. Okay, this is the focus of our lecture, is how to sketch the root locus. There are some fundamental rules or method, and using these methods we can plot the root locus. First one is, first of all, when usually open loop transfer function is given, one point is that there is open loop transfer function is given. First point is, and there is negative feedback. We are usually using the negative feedback. And third important point is, when there is some open loop transfer function is given, then we normally consider that there are more number of poles than the number of zeros. It means open loop transfer function is some proper fraction, and usually it is in the form of product. So by using some these fundamental assumptions, we will using some these techniques or rules to sketch or draw the root locus. First one is, how many number of branches are there? For example, we okay, this is the maximum of the number of poles and zeros, but we are assuming that there are number of poles are greater. Then we say that number of branches of the root locus is equal to the number of the poles, because in open loop transfer function, starting of root locus is the poles position in an open loop transfer function. So it is a first point. Second, as we see in the previous two examples of camera tracking and other example, that it is always symmetric about the real axis. This is the real axis. First of all, we have to place the poles of a given open loop transfer function, and horizontal is the real axis and vertical is the imaginary axis. And if there are some poles here, and the position of these poles are changing with the variation of k, and starting is when k is equal to 0. K is equal to 0. So root locus is starting from the k equal to 0 and ends at k equal to infinite. And it starts from the open loop poles and ends at the open loop zeros. And the second main key point rule is, it is always symmetric about the real axis. And third point is, when we change the values of k, or in a reverse way, if we say that we are talking about the left of the considering pole are 0, then we can maybe take the reverse of that statement, and it will be clear automatically by taking some real example. And next, it is already clear that always it is starting, root locus is always starting from the poles of open loop transfer functions and adds and the zeros of the open loop transfer functions. And this starting and ends is maybe finite point, maybe infinite point. But if we taking our assumption that number of poles is always greater than number of 0, then starting point of the pole in open loop transfer function is always finite. And because end point may be, for example, there are 3 poles and there are 2 zeros, and there are 2 zeros. One pole is end at the open loop 0, and other pole is also ends at the other open loop 0, and the one pole is ends at the infinite. It's uh, it will be maybe follow of the some symmetric maybe follow the some asymptotics. Asymptotic we will define in the next part. And we can understand the concept of behavior at infinite by using finding the centroid, and if it is not following the concept that it is ending at zero, if it is ending at infinite, then it follows the asymptotic lines. And uh, and this is the way to find the centroid and the angle of that centroid. And keep in mind, this is the basic definition. If there are some number of the finite poles, we are talking about the open loop poles. One is at -1 and other is at -2, and sum is -3. Similarly, and this is the sum of zeros. For example, there is only one zero which is lying at -3, and it is the sum is -3. So it is +3 and equal to 0. So centroid lies in this case is equal to 0, and it is divided by the difference of the number of finite poles. There are two poles and there are finite 0 is 1, so difference is 1. And this is the way to find the angles. And 2k, and k representing the numbers, and it depends on the difference of the number of poles and the number of zeros. And we will see in the maybe a detailed example in the next lecture. Maybe we can take some simple example to understand this concept, but these concepts extensively discussed in the next lecture. Okay, keeping these statements are the rules, and draw the root locus for this open loop transfer function. It is k gs times h of s, and the open loop transfer function is given by this one. First of all, we have to plot in a complex plane, and 0 is at -2, and other pole is at -3, and other pole is at -4. First of all, we place these. How many branches are there? There are two branches. One starting from this one, and it means when we take k is equal to 0, and this is the open loop pole, and this is, and again this is the position of the open loop pole when k is equal to 0. And it is always asymmetric, and it definitely is symmetric. And where these lines are lying, this is the important point, and the rules how we can decide. If we are talking about this 0, and the right side of this 0 there is sum of these zeros, and the poles are equal to 0. And if we take this pole -3 and counting the sum of the zeros and poles on the right half of this one is equal to 1, which is odd. If we take this odd, it mean this line segment is lying between these 2 points, and there is a root locus line is here. And similarly, for this pole and for this pole, there is no line of root locus between these two poles, and other line is lying and this in this region. So these are the starting points of the poles. These are the starting points of the poles where k is equal to 1, and one line of this root locus, one path is ends at k equal to infinite, and here this is the 0 which is at -2, and other is lying at k equal to infinite. So this is the starting and end points. So there are two root locus lines. One is at starting from -3 pole and at -2, and other is starting from -4 position of the open loop pole and at infinite. And there is no need to find the centroid, and this concept will be understand inshallah in the next lecture. And the summary is very clear. We are extensively understand the concept of root locus and compare the open loop and transfer functions and how we can calculate and what are the some properties related to these root locus. And at the end we define some rules which will be helpful to sketch the root locus and try a simple example to understand these concepts. Thank you so much.